All right, guys. So what we're going to do today, we're going to start looking at resistors in parallel. Up to now, in terms of calculating resistance, we have been using series, like circuits in series. As you can see here, we do have a parallel circuit, and the rules are different. They're different in some very distinct ways. But the key thing I'm going to need you to pay attention to for this kind of whole lesson is keeping these two in line here. The way voltage behaves in a parallel circuit and the way current behaves in a parallel circuit. And the reason I say this is because they are exactly opposite of what happens in series. So up to now, for example, we would have a series circuit, and I'll just do a quick one here. Something like this. Let's say I've got two light bulbs in series, and let's say that this one is 10 ohms, and let's say that this one is 5 ohms. Okay, and let's just give it a, I don't know, a 6-volt battery. So up to now, what we've done, since we've been dealing with a single pathway where electricity is flowing along one pathway, any resistor that it encounters is going to affect our overall circuit. So if I look here, what we've done up to now is whatever resistor is in the pathway, we simply add them up. We sum those resistors, and that will give us what we call our total resistant or our equivalent resistance. So in this one, I would see that I'd have to go through a 5 ohm and a 10 ohm resistor. So I would simply say that my total resistance was 15 ohms. It's nice and easy, worked fine. And then we were able to go through and solve for all of the other parts of the circuit using our understanding of Ohm's law. Now, with parallel, while it's not difficult, it is far more involved than simply adding these resistors together. So that's what we're going to focus on today. But what you're going to need to watch for is not confusing the rules we use for series with parallel, because that's going to get you into trouble. Okay, so let's go ahead and do a sample problem. Now, as we do this, I will point out how it's different than series and just kind of some places where you want to watch out so you don't get tripped up. But first and foremost, let's have a look at the rules over here. So for parallel, voltage behaves this way. In a parallel circuit, the voltage is going to be constant throughout the entire circuit. All right. Now, this was true back when we did series. This was true for current. It was current that would be the same throughout the circuit. But in parallel, it's not. It's voltage. So if I know the voltage somewhere in this circuit, then I know the voltage everywhere. All right. Now, the second thing we need to keep in mind is current, the way that behaves in a parallel circuit. Remember, in parallel, we have multiple pathways. We are no longer limited to one pathway for electricity to flow. So where series was limiting in that the current had to be moving at the same speed everywhere because of one pathway, in parallel, we have other options for electricity to flow. So we can have some variance in our currents. So as a result, current in a parallel circuit is going to be shared. So that means, let's say we find out, as we'll do here in just a minute, we'll find out our total current of the of the circuit. But when we go and look for individual currents on these different branches, we'll see that they're going to be less than the overall current, but when we add them together, they'll equal the same number. All right. Something here that's going to be new for us, and we'll start right out of the gate with this. We have a new formula. So if I look over here, resistors in parallel. Now, it might look somewhat familiar to when we had resistors in series. If you remember, resistors in series stated that the total resistance is equal to the sum of all resistors in the circuit. And we wrote it this way. RT was equivalent to R1 plus R2 plus R3 and so on, however many resistors you had. Now, when we look at parallel, it is different. We have these in a fraction form now, and we have our R1, R2, our representative resistors, we have them in the denominator of a fraction. So we'll look at how that affects the way we do these problems. So if I am starting with this parallel circuit, okay, I've got two branches. I have a 12 ohm resistor on branch 1, and I have a 24 ohm resistor on branch 2 with a 24 volt battery, okay? the first thing we're being asked to do is to find that total resistance. So right out of the gate, we're going to go ahead and practice with this new formula. So step one, and let's see, where should I put my steps? I'll put them right here. So step one is simply going to be to substitute in your values, like your resistor values, into the formula. So I'll call that sub values into equation. Okay, we're going to take this one thing at a time. All right, like I said, it's not difficult, but because it can be confusing coming directly from series into parallel, I want to kind of walk through this slowly. So we'll sub our values into the equation. So here's my equation, 1 over RT. In other words, the way this reads over here, by the way, is the reciprocal of the total resistance is equivalent to the reciprocals, or the sum of the reciprocals of each resistor in the circuit. So over here, I've got 1 over RT. Resistor 1 for me was 12 ohms, so I'm going to substitute that 12 ohms in there. Resistor 2 was 24 ohms, so I'll put that there. And we don't have a 3 or 4 or anything like that. Ours stops at 2 resistors. All right. Now, starting tomorrow, I will show you guys when you have a situation where you've got 2 resistors in parallel, there is a kind of a shortcut you can use there. But since we're just learning this new formula today, we're going to go ahead and use our formula that you see here. Okay, so adding fractions, it's probably not your favorite thing in the world to do, but it's really not that bad, especially, you guys have your calculators today, and there's no harm in using that tool to help solve these problems. So you could do this the old-fashioned way, right, where we see our 2 fractions, we need to find a common denominator, and then we can go from there. So for example, common denominator here would be 24. So I would rewrite this as 2 24ths plus 1 24th, and that would give me 3 24ths, okay? Now 3 24ths we can simplify, and that would simplify down to 1/8. But, like I said, since I know most of you guys will be using a calculator, I'll just do the example with the calculator, okay? So if you've got a TI like this, you can directly enter fractions into here. You don't even have to use the special fractions key. Like, for example, what I mean, if I wanted to add 1/12 and 1/24th, let me see if I can bring this up closer so you can see the screen. I don't need to use the special feature where I'm putting one number over top of the next. Just simply take 1 divided by 12 plus 1 divided by, 24? Divided by 24, and enter it that way. And I get 0.125. All right, so I've plugged them in and I've added them up. All right, so this brings me to step 2. So once you've subbed in your values, and I wish I'd stopped for a second, but whatever, we've subbed them in, and step 2 is simply to find the sum of the resistors. So you're going to calculate the sum. So in other words, you're going to add those resistors together. Now, when I added it this way, my calculator is set up to give me a decimal response. Okay, just my answers will come in decimals. So I got 0.125. And perhaps your calculator, you've got it set up in that mode, and you got this. And great. Now, if you put that in and you got 1/8, that is also exactly correct. These two numbers are equivalent to one another. 0.125 is the decimal format for 1/8. Okay, so we're going to look at this both ways. I'm going to start with 1/8 because I think it's a little bit easier. So looking at what we got, we've subbed our values in, then we calculated the sum. So this is what you'll do: plug in your numbers, add them up. You're going to get an answer. Now, a lot of people make the mistake of stopping right there and thinking that, oh, there's my resistance. They write it on and they move along. They're missing the last step. So sub them in, calculate the sum, and the final step, step 3, is you need to take the reciprocal of the answer you got here. So take the reciprocal of sum in step 2. I guess I should say the sum from step 2. So what this looks like, now you guys learned about reciprocals a while ago, but just to refresh you, a reciprocal is you take a number, like in this case, I have 1 over 8, 1/8. All right. The reciprocal of 1/8, what we're asking you to do is to invert the numerator and the denominator. So here, 1 is my numerator, 8 is my denominator. If I want the reciprocal of this, I simply am going to flip those numbers. So this would give me 8 over 1, or in simpler terms, just 8. If you remember back in, I believe, probably elementary school, when you were learning about whole numbers, if I said I had the number 8 and I asked you to write 8 as a fraction, saying 8 is the same thing as saying 8 over 1. Okay? So when any whole number you have, you can put it over 1, and that's just its fraction form. So when we take the reciprocal of that 1/8 that we got, shouldn't say equals here, 1/8, the reciprocal becomes 8 over 1. But our convention is to leave off that 1 from the bottom. That's not something we're in the habit of writing. So we would just call it 8. So for this particular question, my answer would be 8 ohms. All right. I plugged in my values. I added them up. I got 1/8. Then I took the reciprocal of that number. And that is my total resistance. And it makes sense because if you look here, before I go into the decimal, when you did this math, you got 1 over RT equals 1/12 plus 1/24, and that equaled 1/8. So in essence, what we're looking at here, we've already done this math and we've gotten this answer. So I could rewrite this as 1 over RT equals 1 over 8. This isn't my total resistance. If you look at it, this isn't saying that at all. This is saying the reciprocal of my total resistance is 1/8. So if I want to find out what my total resistance is, I need to flip that. And that's what we do. And what that leaves us with is RT over 1 equals 8 over 1. And like I said just a moment ago, we're not in the habit of showing the 1 under there. So my total resistance would be 8 ohms. I know that seems a little bit weird. And compared to what we've been doing, it does seem a little weird. But it's nothing too bad. So now, the other number that we got here, you saw in my calculator, it gave me back a decimal. And again, that's fine. A lot of times, all you'll have is like your phone to use a calculator with. So you're going to get decimal responses anyway. So we need to learn how to deal with those. So 0.125 is what I got when I added those up. So I plugged them in. I added them up. I got my sum, which was 0.125. And now I need to take the reciprocal of this number. Now, that might not seem super obvious because usually when we're talking about reciprocals, people think of a fraction and they're flipping it over. But remember, saying 0.125 is the same thing as saying 0.125 over 1. So what we do when you get your decimal answer, you want to take the reciprocal. You want to take 1 over 1/5. 1 divided by 0.125. And let's see what we get when we do 1. Let's see here. 1 divided by 0.125 is going to give you 8. The same thing as when you got 1/8. Because like I said, 0.125 is the decimal equivalent of 1/8. So we would say we have 8 ohms for a total resistance. Now, I get it for those of you who are looking right now and seeing, okay, I've got 8 ohms total, but how can that happen? Because over here, I've got 12 ohms right there, and I've got 24 right here. Like, how is that even possible? How can I end up with a total resistance that's less than even one of my resistors over here? Now, this is something we'll discuss in depth in class, but what you're going to find is that as we add resistors in parallel, remember one of the benefits of parallel is that electricity has multiple pathways to flow through. So if I'm looking at any individual branch, electricity is flowing through this circuit. But if we were looking at it from the point of view of an electron traveling through a circuit, if I'm an electron, I'm either going to go through this first branch or the second branch. I'm not going to go through both. All right. If I added a third branch, that would be adding in even another pathway for electricity to go. So essentially, you can look at parallel circuits and adding branches, adding resistance to these as opening up new lanes of traffic. The example I was giving in class is that if we were, if you've been on like those country roads where there's like one lane going that way, one lane going this way, and you've been lucky enough to get stuck behind somebody in like a piece of farm equipment, like a tractor or something, going like 10 miles per hour up the road. Traffic gets backed up really quickly behind something like that. And then what typically happens is you're going up, and then for a little bit of the stretch, it'll open up into a second lane. And then traffic just starts flying past that. Just opening up that second lane, or kind of like opening up a second branch in the circuit, gives electricity another way to go, and everybody's not bottlenecked behind one point. So as we move forward, you'll see that as you add resistors in parallel, the overall resistance will drop. It's the opposite of what we see in series. In series, remember, the more resistors you add, the greater the resistance gets. All right? And we'll use that to our advantage when we are doing some calculations and building some circuits in here. Okay, so we've taken care of the new part. All right? We used our new formula, we subbed in our values, we added them together and got an answer, and then that all-important last step, we took the reciprocal of that answer. And that's going to be our total resistance. All right, so now going through the rest of these is no different than what we've been doing. You do have to remember, though, your rules. Up to now, like this past week, we've been doing everything in series. So with series, remember, it was current was the same everywhere and voltage was shared. Parallel flips that around. Now it's going to be voltage that's constant everywhere and current is shared. So let's go ahead and work down these and see what we get. All right. So I'll erase this. We've calculated our total resistance there. They want us to tell them the total current. Right. Now, if we look up here, Ohm's law, if I want to know my total current, I need to know voltage and I need to know resistance. And I need to divide voltage by the resistance. So if I'm looking here, now look, we're looking for total current. All right. That's for the whole circuit. So I equals V over R. My voltage for this circuit is 24 volts. So I'll go ahead and put that in. My resistance for the whole circuit, we just calculated that, right? That's 8 ohms. So we'll divide it by 8 ohms. When I do that division, we get 3, and the unit for current, remember, is the amp, or the ampere. So we have 3 amps of current in this whole circuit. All right. Let's go ahead and erase this for a moment. Now, again, I want to bring your attention back to the rule changes we're dealing with now. I have 3 amps. When we were talking about series, that meant it would be 3 amps everywhere. That's not the case anymore. We have 3 amps in this circuit, but it's got to be shared amongst 2 different branches. So these should end up being less than 3 amps each, but when we add them together, they'll equal this 3 amps. So let's have a look and see what happens. So we've got our resistance, we've got our total current. Now we're going to look at our voltages. So V1, remember that little subscript, that 1 is corresponding to a resistor in the circuit. So if I come over here, V1 is going to correspond with R1. So I want to know my voltage at this resistor. Okay? So let's have a look and see what we know about it. I know, and I'm going to go ahead and plug in my total current now. Let's act as if we're putting a little ammeter in here. And we'll say we've got 3 amps in the whole circuit. All right, so I know I have 3 amps in the whole circuit. I know I have 24 volts here. You might be tempted to come over here and be like, oh, well, if I just want to know my voltage, that's going to be my current times my resistance. So that's going to be 3 times 12. And you might think 36. And that's going to be a problem, right? Because first of all, 3 times 12, 36, that's more than the battery's putting out. So that's not going to work out. But that's a sign that you're forgetting our rules over here. When we're talking about voltage in parallel, it's the same everywhere. So if you know the voltage anywhere, you know the voltage everywhere. So if I see here, my battery is providing 24 volts. So that means wherever I go in this circuit, I'm going to have 24 volts. So V1 will be 24 volts. If we come down here, V2, which is over here, that's also going to be 24 volts because of what we understand about voltage. Remember when we were building these circuits, parallel circuits tend to have the brighter bulbs. If I have the same battery pack going in there, my parallel bulbs are going to be brighter because they're receiving the full voltage. While when we did series, that voltage was being shared by everything in here. And here, that's not the case. So nice and easy, just knock out the fact that we've got 24 volts on both of those. That's leaving us with the last two. They want to know the current at resistor 1, and we want to know the current at resistor 2. Okay? So let's come back up here, just again to remind ourselves, if I want current, cover that up. That's going to be voltage divided by resistance. So now what we got to pay attention to, we're no longer looking for the total current. I'm looking for I1. So what I like to do when I'm drawing these here, I'll actually label what I'm using. So I need current for location 1, for resistor 1. So that means I'm looking at resistor 1. And my voltage is my voltage because we're in parallel. So if I come here, all right, my voltage at this point is going to be 24 volts. And I'm going to divide that by my resistance at resistor 1, not my total resistance. Okay? I'm looking specifically at this location. So at R1, I've got 12 ohms. So that is going to get plugged in right there. When I do this operation, I get 24 divided by 12. That's going to leave me with 2 amps. So my current at R1 is 2 amps. Okay? And you can do a quick check for yourself. You're like, all right, I've got 3 amps total in the circuit. I'm using up 2 of them with that first resistor. And when you look at it from this, you can very likely deduce that, oh, well, that means there's only 1 left for this other one. And that's great. You know, in this case, it's correct. And you could do that deductive type of reasoning. The only thing I'm going to caution you against there is that only works. This deduction where you're like, all right, I've got 2 amps. There's 3 total. That leaves 1. Great. That only works if you got this right. If you made a mistake here, then that sort of thinking is going to cause you to make a mistake here too. So I find it's always best to go through the calculation and just make sure, because that could present mistakes made earlier that you can catch. All right. So let's go ahead, look at current for I2. That's over here, right? So it's going to be voltage divided by resistance. Voltage is 24 volts. Resistance here is 24 ohms. I do this division and I get 1 amp. All right. Now the way we can check this, the sum of my 2 currents, remember I've got 2 branches here, so I'm just looking at my current in 2 locations. The sum of those should equal my total current, which we come back up here and we see that it does. 2 amps and 1 amp summed together give us 3 amps. Okay? Now these problems are all going to be like this. Okay, some variant. You know, maybe they won't give you the voltage on one, but if that's the case, then they're going to give you the current and you can figure the voltage out from there. The hardest part about any of this, number one, is just taking your time. Please don't try and rush through these. You're just going to frustrate yourself. But keeping this in order. This is exactly opposite of series, and that can mess you up. That's just how it is. All right, you do enough of them, and you'll start to um, get more comfortable, kind of switching modes between series and parallel. Um, but for now, we're going to stick with these for the next several days, and then we'll start to kind of blend the two. We'll have some series portions in a parallel circuit, for example, and we'll kind of blend them together. But for now, just to recap, the new thing today was our formula for resistors in parallel, right? So it's where you take the resistors from your circuit and you sub them into your formula, like R1, R2, and so on, and then you're going to add those up. All right, you're going to get an answer. Whatever that answer is, remember, you have that third step where you need to take the reciprocal of that answer. Okay? Now, the only other thing I'll mention, and if this doesn't apply to you, it's fine. You don't have to keep watching. But if you don't, let's say you don't bring it like a TI calculator or something that can deal with fractions with you to class. I'm going to erase this for a moment. If you only have, say, like an iPhone with you, all right, just like your phone, and you can use the calculator on that. Let's see here. Let's pull a calculator up. Just your typical Apple or Android calculator. And I'm going to plug these back in. I just want to show you how we can do one of these. So I'll put everything back in the formula. 1 over RT equals 1 over 12 plus 1 over 24, right? And that's going to equal something. Now, if your phone doesn't handle fractions, we can easily do this still. All you need to do is take the fraction and convert that into a decimal. Once you do that, add it just like normal and take your reciprocal. So let me show you what I mean. So for the first one, 1/12. The way you can turn a fraction into a decimal is simply doing the math. 1 divided by 12. So if I say 1 divided by 12 gives me 0.083 repeating. So I'm just going to put that beneath this for this example. So it's going to be 0.083 repeating. Now, I am cutting this off, so we're rounding a little bit. So our final answer will need to round, but that's okay. So I've got that, and I'm going to need to add that to whatever this is as a decimal. So let's try that. It's going to be 1 divided by 24. Hopefully you can see that. 1 divided by 24. And that's going to give me 0.0416, repeating for a while, and then we get to 7. So let's say 0.0416. Let's just stop there. 0.0416. So I've converted my fractions into decimals. That's all I've done. Now what I'd like to do is add them together. So let me take that there. I still have that answer there, so I'm just going to add the first one to it. So that plus the 0.083. Let's see here, 0.083. And I'm going to get 0.1246. So let's take that. We'll take it to 3 decimal places. 0.1246. That's going to round to 0.125. And that number might look familiar to you from earlier. Remember, 0.125 is the decimal equivalent of 1/8. And if you remember, that's what we had over here. So we would take that number, take the reciprocal of it. So what I'm going to do is take a 1 over 1.125. I'm going to do my math just to show you. So 1 divided by 0.125 is going to give me 8, which is exactly what we got when we did the problem earlier. Okay?
Good afternoon.
Now,
this is a reminder, 6th grade jazz
all right.
band.
These are more time consuming and these are more complicated. I'm not going to fool you about that, okay? But these are not out of your grasp. You can easily do these. You just need to keep the steps in mind, keep the rules in mind and the steps. This one being the most important, only because that's the one everybody forgets. Okay, so don't be in a rush when you're going through these. Okay, So you take care of that, and then the rest of the problem works just like it always has. We're using Ohm's law under these rules now, though. All right. So I hope this was helpful. This one was longer than the previous ones, but like I said, hope it was helpful. If you have any questions, just ask. I'm happy to sit down with you. We can do sample problems. If you have, questions about, whatever, any of it, just get in touch and I'll help you out. Okay. All right, guys. Have a good one.